I wanted to go through an example to show the sampling distribution of the one sample t-test. This picks up about where I left off last time. I'm using the same example, but I'm changing it a little bit. I'm saying that a researcher wants to test the claim that the mean number of hours of TV watched by college students in the US equals 3 hours. And in a one sample t-test, the null hypothesis says that the population mean does equal the number being tested. So in this example, the null hypothesis would say that the population mean does equal 3. And in this example, we've collected data from a sample of 30 college students from the population of college students in the US. And for each of the 30 students right here, we've recorded the number of hours of TV that each of these students watches per day. And in our sample of 30 students, we've ended up with a sample mean of 2.4 and a sample standard deviation of 1.5. And I'm actually going to change the 2.4 a little bit just to make our example a little bit simpler. It's a little bit of a nicer number. Now we can calculate our t-score for the sample that we collected, or for the sample that we collected data from. Let's see. The t-score for a one sample t-test is the sample mean, which is 2.5 in this example, minus the population mean being tested, which is 3, over on the bottom you have the sample standard deviation of 1.5, and then over the square root of our sample size. Our sample size is 30 because we've collected data from 30 people. And if we solve all of this, we'll get our t-score. First we should get the square root of 30 first. It comes out to about 5.48. And then, so on the bottom we have 1.5 over 5.48. And on the top we have 2.5 minus 3. What do we get on the bottom if we divide 1.5 by 5.48? We get about 0.27. So I'll change the bottom of the fraction to 0.27. Now we need to subtract on the top of the fraction. When we subtract on the top, we get 2.5 minus 3 equals negative 0.5. So we end up with negative 0.5 over 0.27. And then when we divide, we get 1.85, or negative 1.85. So that's our t-score for this sample. And we know that since we've selected a sample of 30 people and we collected data from that sample, we've selected one of the possible combinations of 30 that might be selected from our population. And in this picture over here, you can see all of the possible combinations of 30 that might be selected. If you wanted to find out the number of possible combinations, you would have to go to that combinations calculator and type in the size of the population, which is about 19.7 million for college students in the US, and then type in 30, and it'll give you the number of possible combinations of 30, which would be the number of boxes inside this graph right here. And it would be many, many boxes. But we can actually predict what the shape of those boxes would be, because I talked about how the assumptions of the one sample t-test say that the population that's being sampled has to be normal, or the number of, or your sample size has to be 30 or larger. This is one of the assumptions. And then if the population is normal, if the population that you've sampled from is normal, which would be all college students, meaning if the TV watching of all college students was a normal curve, or if your sample size is 30 or larger, that makes the shape of these possible samples bell-shaped or normal. And in order to find out if our possible samples of 30 have a bell shape or a normal curve, we have to find out if one of these two things is true in our example. We're not sure if the population that we sampled from is normal, but we know we do have a sample size of 30 or larger because we've collected data from 30 people. So since we've satisfied the sample size of 30 or larger, we know that these possible samples will be bell-shaped. And if our sample size wasn't 30 or larger, for example, if we only collected data from 20 people, then we would have to make sure that we sampled from a normal population, because if the sample size is below 30, then these samples will only be normal if the population that they came from is normal. But if the sample size is 30 or larger, then the possible combinations are always bell-shaped. So we know in our example that our possible samples of 30 are bell-shaped. But we're not sure what the population mean equals. We're testing whether it equals 3, but we're not sure that it equals 3. And we know that the population mean is always at the center of the possible samples, especially when the samples are bell-shaped. So whatever number on the number line that lines up with the center right here will be the population mean. So if our population mean was 2.5, that would mean that the possible samples would be centered at 2.5 right here. And if the population mean was 3.5, then the possible samples would be centered over here. But at the beginning of our study, we're assuming that the null hypothesis is true, which means we're assuming that the population mean actually is 3. So we're assuming that our possible samples, or this set of possible samples, is centered at 3, with a population mean of 3. And so we're looking at a hypothetical situation here where the set of possible samples or combinations is centered at 3, means we're looking at a situation when the population mean is 3. And we know that the samples that fall around our population mean are bell-shaped because our sample size is 30 or larger. Now that we have this curve, or this distribution of possible samples that would exist in the situation where the null is true, where the population mean is 3, we can look at how extreme our sample is inside of this situation. Our sample has a mean of 2.5, which means we selected one of these samples right here that's stacked above 2.5, meaning we selected a sample with a mean of 2.5. This number line is showing the means of all the possible samples. And all of these possible combinations of 30 that might be selected has a sample mean and a sample standard deviation. And also each one of them has a standard error, or each one of them has an estimated standard error. Let's say we got this sample right here with the x. Our sample has a mean of 2.5, and let's see what the estimated standard error of our sample is. The estimated standard error is the bottom of the t formula, which is s over the square root of n. Which is 1.5 over the square root of our sample size, which is 30. The bottom of our t formula came out to 0.27, which means our standard error is, our estimated standard error is 0.27, but I'm going to actually make it to, 0.25 because it'll be a simpler number for our example. So now we know our sample has a mean of 2.5 and an estimated standard error of 0.25. So each of these possible combinations will give you a sample mean, an estimated standard error, and a t-score. Our sample right here with the x gave us a t-score of negative 1.85. Let's look at one of these possible samples over here at the right end. First, let's see how extreme our sample is inside of this curve. Our sample is actually fairly extreme because our sample is about 2 estimated standard errors below the center. Our center is at 3, and our sample came out with a mean of 2.5, and our estimated standard error came out to 0.25, meaning we have about 2 estimated standard errors between the mean of our sample and the population mean that we're testing. So we can put 2 of these bars for estimated standard errors. And since we're about 2 estimated standard errors to the left of the center, that's why the t-score of our sample came out to about -2, because the t-score shows the number of estimated standard errors between the center and your outcome, which is our sample mean in this case. And an outcome that's 2 estimated standard errors away from the center is actually a fairly extreme outcome. A sample that's 3 standard errors away from the center is even more extreme. What if we got a sample out here, which is at about 3.5? Not quite, but let's just say it's 3.5. And let's say that the estimated standard error of this sample comes out to 0.5, which is a little bit low. What would the t-score of the sample equal? Well, the t-score is the number of estimated standard errors between the center and the outcome that you found. So we have to think, how many times does 0.5 fit in between 3 and 3.5? Well, you have 3 up to 3.25 is one of the estimated standard errors. And then 3.25 up to 3.5 is another estimated standard error. So it's actually 2 estimated standard errors above center, which would mean that this sample would have a t-score of 2, positive 2. And let's look at this outcome down here. It has the same sample mean because it's stacked right below this other sample that we just looked at. So this sample over here with the x would also have a mean of 3.5. But what if it had a different estimated standard error? What if this possible sample gave us an estimated standard error of 1? Now we can find out what the t-score of this sample would equal. If we find out how many times 1 fits in between 3 and 3.5. Well, if the center is 3, then 4 would have a t-score of, this would be 1 standard error, or 1 estimated standard error above center, because now our estimated standard error is 1. But 3.5 is only half of one of these estimated standard errors, because 3.5 is right at the center. So if you calculate the t-score, you do 3.5, which is the sample mean, minus the center, which is the population mean that we're testing, and on the bottom we put our estimated standard error, which goes on the bottom of the t-formula. We're saying that this estimated standard error of this sample is 1. What does our t-score come out to? We end up with 0.5 over 1, which means our t-score comes out actually to 0.5, because 0.5 divided by 1 is just 0.5. So we can see that even if 2 possible samples have the same sample mean, they might not have the same t-score if the estimated standard error is a different number. And what does this mean? Or why is this important? We can also look at how our possible samples or our possible combinations would be stacked, or how they would be spread out over a number line of t-scores. This is the number line of sample means. And down here I'll make a number line of t-scores. 0, I think I'll do 0.5, 1, negative 0.5, and negative 1. Now I'd probably want to go down to negative 2 and up to positive 2. Two is pretty extreme. Negative 2 is pretty extreme. Or, I mean, it's negative 2 and positive 2 are starting to become extreme. These are pretty much the cutoff for an extreme value. So anything above positive 2 and anything below negative 2 would be considered extreme, usually. So we can see up here that these samples that are stacked above the same sample mean might not be stacked above the same t-score, because this sample right here has a t-score of 2, so it would be moved up here to 2. This sample mean has a t-score of 0.5, so it would be moved down to 0.5, which would mean in the t-score graph, these sample means that are stacked above each other are often separated from each other. They're not stacked on top of each other anymore once you put them above the t-score number line. And what that does is it actually distorts the normal shape, because when samples are starting to be moved to the left or up to the right because of these estimated standard errors, the shape turns from a normal shape, which we have up here, into something called a t-distribution. And a t-distribution is it's often shorter and flatter than a normal curve, even though it's still symmetric. Right now, I'll just put our possible samples above their t-scores, or I'll just draw a graph that shows our samples stacked above t-scores. I might not make as many boxes this time. These are the same combinations of 30 people that we have up here. It's just now each combination is above its t-score instead of above its sample mean or above its x-bar. And all of the samples that were stacked above 3, which were stacked above the population mean being tested, those will all be stacked above a t-score of 0, because whenever the sample mean perfectly lines up with the population mean being tested, what do you always end up with a t-score of 0. Let's look at one of these samples. Sample mean is 3 because it's stacked above 3. And if we calculate a t-score for this sample up here at the top, when we subtract the sample mean of 3 by the population mean being tested, which is 3, and we divide, it doesn't really matter what the bottom of the t-score equals, because the top of your t-score formula will come out to 0, which means the t-score has to be 0, no matter what the estimated standard error comes out to. That means that all of these samples stacked above 3 will have a t-score of 0, no matter what the estimated standard error equals. And the more extreme samples will be further away from 0. I'll put some more boxes in here. The boxes would actually go past 2 and below -2, but I won't draw all those boxes out. I just need to put a few more in here. Our sample had a t-score of -1.85, so our sample of 30 would be about right here. So we could say that this might be our possible sample of 30. And once again, there would be many more boxes in here than what I've drawn, because there's many combinations of 30 that can be taken from a population of 19.7 million. So here's our sample stacked above its t-score. And the curve that outlines these t-scores is called a t-distribution curve. And its shape is actually predictable based on the degrees of freedom. So let's see what our degrees of freedom equals for our t-test. We've collected data from 30 people, and in a one-sample t-test, the degrees of freedom is n-1. Our n was 30. So 30 minus 1 would equal 29, which would mean that we have a curve that outlines our possible samples above their t-scores would be a t-distribution with a degrees of freedom of 29. And in order to know the exact shape of the t-distribution curve, you have to know what the degrees of freedom equal. Because when the degrees of freedom is a higher number, the t-curve is more bell-shaped or more normal. And once you get up to about 29 degrees of freedom, that's the point when the t-scores are pretty much bell-shaped, just like the sample means are. And so our t-scores would be pretty much bell-shaped because we're looking at combinations of 30. But in order for your t-scores to follow a t-distribution curve, you have to have a normal. The sample means have to be normal. or the t-scores won't follow the t-distribution curve. So first we have to make sure that our sample means are normal. And that happens if you're sampling from a normal population, or if your sample size is 30 or larger. If you have one of these two things, your sample means are normal. And if your sample means are normal, your t-scores, or the t-scores of the combinations, follow a t-distribution curve. And the exact shape of the t-distribution curve depends on the degrees of freedom, which is 29 in my example. And the reason it becomes more bell-shaped with higher degrees of freedom is because when the degrees of freedom goes up, that basically means the sample size is going up, because the degrees of freedom is n minus 1. So higher degrees of freedom means a higher sample size. And when the sample size goes up, these estimated standard errors of the different samples, they become closer to being the same number. When there's only a small number of people inside each combination, the different estimated standard errors of the different combinations will vary a lot and have widely varying numbers, which will distort the shape of the t-curve more. Because when the different estimated standard errors vary more widely across all of these possible samples, the t-curve gets distorted more, because that's what the distortion is coming from. The distortion is coming from these different estimated standard errors. But when the sample size, or the number of people in each combination, gets larger, these estimated standard errors get closer to being equal. You get closer to being at a point where each sample will give you the same estimated standard error. And once you have about 30 people in each combination, you reach the point where these estimated standard errors are pretty close to being the same number, which means you don't really have any visible distortion in the shape of the t-scores, meaning the shape of the t-scores pretty much follow the same bell shape as your possible samples. What else do I need to say? We're looking at a situation when the null hypothesis is true, because we're looking at a situation where the center of our curve is at 3. And we're looking at how extreme our sample that we've collected is inside of this situation where the null hypothesis is really true. This center value, which is the population mean being tested, is actually called a null value. Because the reason it's called a null value is because it's the value, or the number, inside of the null hypothesis, right over here. So when you're looking at a situation when the null hypothesis is true, the null value is at the center of the curve of the possible samples. And if the null value is at the center, that means in this curve down here, the center is at 0, because when this peak right here lines up at 3, which is the null value, the peak down here with the t-scores lines up at 0. And 0 is actually the point where you have no evidence that the null hypothesis is wrong, because I said that larger test statistics give you more evidence that the null is wrong. So all of these samples stacked above 30, what am I saying? Not 30, all of these samples stacked above a t-score of 0 right here are showing no evidence that the null is wrong, because they're lining up perfectly with the null value. And the combinations that are further away from the null value, or further away from the t-score of 0, are the samples that will show you more evidence that the null is wrong. And At a certain point in this t-score number line, up here somewhere, you'll have the critical value. Somewhere on this t-score number line will be the critical t-score. Critical value. And if you end up with a combination of people, or if you end up selecting a combination of participants that gives you a t-score beyond the critical value, meaning if you end up with a t-score somewhere up here, that's when you can reject the null hypothesis. So if I've ended up collecting data from this sample up here that gave me a t-score above the critical value, then that means that I'm allowed to reject. But if I've selected an outcome down here below the critical value that gave me a t-score that was too low, that's when I can't reject. So this outcome down here would make me fail to reject the null hypothesis. And this area inside of the curve where you're allowed to reject the null hypothesis, or this area above the critical value that contains the combinations that let you reject the null hypothesis, this shaded area is called a rejection region, or the rejection region of the curve. It's the section of the curve that contains the possible combinations that will give you a t-score at least equal to or above the critical value. And this is where the researcher wants to end up, because they want to get a combination of participants that lets them reject the null hypothesis. And I think this explains all of the concepts that I wanted to explain for the sampling distribution of a one-sample t-test. I think I explained how the t-score is showing the number of estimated standard errors between the sample mean and the center value, which is the null value. So this sample up here gave us a sample mean of 2.5 and an estimated standard error of 0.25, which meant that it was 2 estimated standard errors above or below the center, which gave us a t-score of about -2. This wasn't actually 0.25, it was actually 0.27, and I rounded it. So when you calculate the t-score, what you actually do is you take the estimated standard error of the sample that you collected, and you calculate the number of times that estimated standard error fits between your sample mean and the null value at the center. And different samples that have the same sample mean can end up having different t-scores, because if the estimated standard error is different, then that changes the number of estimated standard errors that fit in between the sample and the center. If your estimated standard error comes out to 1, you'll have a smaller number of estimated standard errors in between your outcome and the center, because the bar, when you have 1, the standard error bar becomes wider or longer, which means not as many standard errors fit between your outcome and the center. When your estimated standard error comes out to a smaller number, these standard error bars shrink and become smaller or narrower, which means more estimated standard errors will fit between your outcome and the center. That's why these two samples that both had an X bar or sample mean of 3.5 gave us different t-scores. This one came out to 2 because it had a smaller estimated standard error. This one only came out to 0.5 because it had a bigger estimated standard error. So I hope this video is helpful. I'll see you in class.